6.2 notes are all about the evidence for evolution. So you will actually need your book for this one because we are going to look at some of the diagrams in your textbook. So get your books open to page 374. Everybody should have brought their textbook home with them. So the first piece of evidence that we have for evolution is fossils. Fossils can show us how species have changed over time. We know that we found fossils in amber and frozen fossils in ice and lots of fossils found in sedimentary rock. We know the law of superposition that tells us the deeper in the ground, the older it is. So we know the farther down, generally speaking, the farther down we find a fossil, the older that fossil is. And we can see how organisms have changed over time by looking at how the fossils have changed over time in that species. So the fossil record, should all be review for you, but the fossil record just says that all of the fossils that have ever been discovered are all in one place and they're all put in order. We do have lots and lots of gaps in the fossil record for periods of time that we don't really have evidence of what lived or what an organism might have looked like in this intermediate gap of time. However, we can use the fossil record to make predictions that, in this empty space of time, I know that there was probably an animal that could walk on land but also live in the water, kind of like an amphibian. We also can see that the more closely related two organisms are, the more similar their bone structures and body structures are. So we can see a lot of similarities between mammals, like the wing of a bat is very similar to the hand of a human because we are both mammals, whereas the wing of a bat is very different from the fin of a fish because they're not in the same family at all. This is a video just about how fossils can provide evidence for evolution. It's in the YouTube playlist. So the first piece of evidence for evolution is our common ancestors that we have. A lot of people want to just say, okay, well, humans came from monkeys. We're not going as far as saying that, but humans and monkeys had a common ancestor. That means somewhere along the tree of life, the history of the tree of life, we had a common ancestor way, way back on our branches. So you can see here that primates and rodents have a common ancestor right here. And then if you go even farther back, maybe we have a common ancestor with crocodiles and dinosaurs. And if you go even farther back, we have a common ancestor with amphibians. Okay. So common ancestor is just what we call just the most recent version of that animal where we had two different species come from. There's also what we call vestigial structures. Vestigial structures are, that term is not in your book, but the concept is. So the vestigial structures are the things that we have in our body that we don't really need anymore. They're not really fully formed anymore, but they're still there because an ancestor at one point needed it. So a really good example of this that our book goes through are the pelvic bones in whales. Pelvic bones are like the hip bones that you and I have that hold our legs to our bodies. Whales also have a pelvic bone. It's kind of small and it's not even really attached to its spine anymore, but it's in its body because whales have an ancestor that at one point had legs and needed that pelvic bone to hold its legs onto its body. But over time, that pelvic bone wasn't really needed anymore, so it started being reduced in size, but it's not really hurting the whale to have it, so it hasn't evolved out. Humans also have a lot of vestigial structures. One is our tailbones. Our tailbones were obviously used because at one point our ancestor way, way back had a tail and needed that tailbone to hold the tail onto its body. We still have a tailbone. It doesn't really hurt us to have it. but it's a little bit of our spine that extends beyond our hip bones that we don't really need. We also have we have some vestigial teeth called wisdom teeth that grow in a little bit later. We don't really need them, but they exist. And you can see tons and tons of other examples of these in this video that Vox made. It's called Proof of Evolution. You can find on your body. It is also on the Google playlist or the YouTube playlist, but it goes through tons and tons of things that our bodies have, like the muscles that we have that can help our ears twitch. Why do we have those? And this little tendon right here that some people have and some people don't. But all of these things, if you have them in your body doesn't really need it, but your ancestor at one point did. There's another example that I kind of alluded to before. It's called homologous structures. And again, that term homologous is not in your book, but it is important. Homologous structures are just those structures that we can see that are very, very similar from one species to the next. A good example of this are the forelimbs in any mammal. The arm and hand bones in a human are very, very similar to the arm and hand bones in a cat, which is very, very similar to the bones that are in a whale fin, which are very similar to the bones that are in a bat wing. So all of these animals, because they're all mammals, they all have a very, very similar bone structure. They're the same layout. They're just used very, very differently. Humans use our hands very different than cats use their legs, which is very different from how whales use their fins, which is very different from how bats use their wings. But we all have a very similar bone structure because somewhere way, way back, we have a common ancestor that also had that bone structure. Another piece of evidence for evolution is that we all have similar DNA. So similar DNA, if you were to actually look at the differences in our DNA, you would see the actual molecules being very, very similar to each other. So if you look on page 377 in your book, you can see how all of these organisms here, the chimpanzee, the rhesus monkey, whales, turtles, bullfrogs, and lamprey, they all have very, very similar DNA, but the farther back you go, the more differences you see in their DNA. So these are all the number of differences from humans. So chimpanzees, in this particular amino acid that we're seeing, humans and chimpanzees have 0 differences. We're very, very similar. Rhesus monkeys, there's only 1 difference. So again, very, very similar. Whales are also mammals, just like us. So there's only 10 differences in that particular trait. But then the farther back you go, turtles, bullfrogs, lampreys, the more differences you see in those traits. So the question number 11 on page 377 is asking, which 2 species do you infer are the least closely related to humans? And that's bullfrogs and lampreys, because that's where you see the most differences. But the fewer differences you see in your DNA, the closer related you are. There's also lots of developmental similarities that you can see on the bottom of page 377 as well. Developmental similarities just means like as embryos, so either in the egg or in the womb, organisms have a lot of really similar structures. This is a really interesting graphic, I think, that shows how similar different organisms are. It's a fish, a reptile, a bird, and a human. And you can see that in the womb or in the egg, all of these organisms look really, really similar. Our book shows a chicken and a cat having very, very similar structures in the egg and then in the womb. But you can just see, like, going farther back as far as its development, we have a lot of similarities from organisms that look very, very different once they're born and once they're grown. So if you look at page 378 and 379, we can look at all of these different stages of development of whales. This is a really, really interesting evolution that we can see here. It's called in cetaceans. Cetaceans are just like the whale family. So if scientists study whale evolution, if they go farther and farther and farther back and they find more and more and more historic ancestors, they will see that a recent whale, like a whale that lives now, might have a small pelvis, whereas a few hundred or a few million years ago, looks like 40 million years ago, we have whales that have a very, very small hind limb. And then if you go even farther back from that, you can see that that hind limb, that those back legs are a little bit more developed, and those front fins are now looking like they're able to actually support some weight. And then even farther back from that, those legs are a lot more developed and able to walk. And then even farther back from that, it's looking closer to a horse, right? It looks a lot more closer to a modern mammal that we know to live on land. So these transitional characters here in the middle show how a walking land mammal could end up being a whale. The DNA evidence shows that whales are super similar to hippos. And hippos, as I'm hoping that you know, hippos can live both on land and in water. So I'm hoping that this cleared up some of the questions you might have had about evolution and what evidence that we do have for it. Please, if you have questions, don't hesitate to email me or post to that discussion thread, or I will see you at office hours. Thank you.